Hello everyone. Welcome to our latest video tutorial on the fascinating topic of creating deep face models using Python and OpenCV. In this step-by-step guide, we will explore the easiest and most efficient way to delve into the realm of deep face creation. Whether you're a beginner or an experienced developer, we've got you covered. By leveraging the power of OpenCV, a versatile computer vision library, and combining it with Python's flexibility, we will unlock the secrets of generating deep face models effortlessly. So, get ready to embark on an exciting journey of exploring facial recognition, feature extraction, and deep learning techniques to create stunning deep face models. Let's dive in. This tutorial is very simple. It just encapsulates in one file. I will create and name it Deep Face Example Py. Here, the code imports the following libraries. CVWO, OpenCV library, which is widely used for image and video processing. NumPy library, used for numerical computations and array manipulation. MediaPipe library, which provides a framework for building multimodal applied ML pipelines. It includes a wide range of pre-built solutions for tasks like object detection, face detection, pose estimation, etc. Sys, a module that provides access to some variables used or maintained by the interpreter and to functions that interact with the interpreter. These variables define the desired width and height for the video frames. In this case, the width is set to 640 pixels and the height is set to 480 pixels. This line creates a video capture object named cap by passing the file name video, MP4 as an argument. It opens the specified video file for reading frames. This line creates a video writer object named result1 to write the processed video frames into a new video file called output2mp4. The four arguments provided are output2mp4, the file name of the output video; cv2 video writer fork; mp4v, the four-character code representing the codec to be used for encoding the video. In this case, it specifies the mp4v codec. These lines use the set function of the video capture object, cap, to set the width and height of the video capture to the desired values defined earlier. This line reads an image file named messy JPG using the imread function from OpenCV, CVWO, and assigns it to the image variable. The imread function loads the image as a NumPy array. These lines import specific modules from MediaPipe. Here's what each line does. MP-drawing is used for drawing utility functions provided by MediaPipe. MP-drawing styles provides various drawing styles for annotations. MP face mesh is the module responsible for face mesh detection using MediaPipe. This line defines the function getLandmarkPoints, which takes an input image, src image, as a parameter. This line initializes the face mesh object from the MP face mesh module, which is responsible for face mesh detection using media pipe. The arguments provided are: static image mode equals true, sets the object to operate in static image mode. Max num faces equals 1, specifies that it should detect only one face in the image. Refine landmarks equals true, enables refining the face landmarks for better accuracy. Min detection confidence equals 0.5, sets the minimum confidence threshold for detecting a face. This line processes the input image, src image, by passing it through the process function of the face mesh object. Before passing the image, it is converted from the BGR color space to the RGB color space using CVT color from OpenCV. These lines check if face landmarks were detected in the image. If no face landmarks are found, results, multi-face landmarks is empty. The function returns none. Additionally, if more than one face landmark is detected, the program exits with an error message. These lines retrieve the face landmarks from results, multi-face landmarks, and store them in the src face landmark variable. Then, a loop iterates over all 468 landmark points and calculates the corresponding x, y coordinates based on the shape of the input image, src image. The calculated landmark points are stored in the landmark points list. Finally, the function returns the list of calculated landmark points. This line defines the function extractIndex and parArray that takes a numpy array and parArray as a parameter. These lines iterate over the elements of the first dimension and parArray 0 of the input array. The loop assigns each element to the variable num. Since there is a break statement after the first iteration, only the first element is extracted, and subsequent elements are not processed. This line returns the extracted element stored in the variable index. The extractIndex and parArray function takes a numpy array as input, iterates over its first dimension, and returns the first element of the array. It can be useful when you want to retrieve a single value from a numpy array, such as extracting an index or a specific element of interest. This line defines the function getTriangles that takes three parameters: convex hull, landmarks points, and NP points. These lines perform Delaunay triangulation on the specified convex hull using the subdiv2d class from OpenCV. Here's what each step does. Rect equals CV2 bounding rect, convex hull, computes the bounding rectangle of the convex hull region. Subdiv equals CV2 subdiv2d, rect, creates a subdiv2d object using the computed bounding rectangle. Subdiv insert, landmarks points, inserts the landmarks points into the subdiv2d object, defining the points of the triangulation. Triangles equals subdiv getTriangle list, retrieves the list of triangles that form the Delaunay triangulation. Triangles equals NP array, triangles, dtype equals NP in 32, converts the list of triangles into a numpy array of integer data type. These lines iterate over each triangle in the triangles array. For each triangle, it performs the following steps. Retrieves the 3 points, tone, PT3, of the triangle. Searches for the indices of these points in the NP points array using NP, where, and the condition, NP points equals tone, all, axis equals 1, which checks for matching points. Extracts the index of each point using the extractIndex and parArray function. If all three indices are successfully obtained, a triangle list, triangle, is created and appended to the indexes triangles list. Finally, the function returns the indexes triangles list, which contains the indices of triangles formed by the Delaunay triangulation of the specified convex hull region. The getTriangles function performs Delaunay triangulation on a convex hull region and returns the indices of the triangles formed by the triangulation. These triangles can be used for various This line defines the function triangulation that takes three parameters: triangle index, landmark points, and an optional imp. These lines retrieve the three landmark points, TR1 tone, TR1 PT12, TR1 PT3, from the landmark points list based on the indices specified in triangle index. The 3 points are then stored in the triangle array as a NumPy array of integer data type. This line calculates the bounding rectangle, rect, for the triangle using CV12, bounding rect. The rectangle coordinates and dimensions are assigned to x, y, w, h. These values represent the top left corner coordinates, x and y, and the width and height, w and h, of the rectangle. These lines check if the imp parameter is provided. If so, they extract the region of interest, ROI, within the bounding rectangle from the imp using slicing, imp y, y plus h, x, x plus w. The ROI is then assigned to crop triangle. If imp is not provided, crop triangle remains none. This line creates an empty black image, crop triangle mask, with the same dimensions as the bounding rectangle, filled with zeros. It serves as a mask for the crop triangle region. These lines create an array of points, relative to the top left corner of the bounding rectangle. It subtracts the x and y coordinates of the top left corner from the corresponding landmark points, creating points relative to the local coordinate system of the bounding rectangle. This line fills the crop triangle mask with white color, 255, inside the triangle defined by the points using CV12. Fill convex poly. The mask will have a white triangle shape corresponding to the points of the triangle within the bounding rectangle. Finally, the function returns the points array, relative points within the bounding rectangle, the crop triangle, ROI from the input image, the crop triangle mask, mask of the triangle region. This line defines the function warp triangle that takes 5 parameters: rect, point zone, point SWO, SRC crop triangle, and des crop triangle mask. This line unpacks the values from the rect tuple into separate variables x, y, w, and h. These variables represent the top left corner coordinates, x and y, and the width and height, w and h, of the rectangle. This line computes an affine transformation matrix, using the source points, point zone, and the destination points, point SWO. The CV12 getAffine transform function takes 2 sets of points and returns a 2x3 matrix that represents the affine transformation. This line warps the SRC crop triangle image using the computed affine transformation matrix, and the dimensions of the bounding rectangle, w, h, using the CV2 warp affine function. The result is stored in warp triangle. This line applies a bitwise an operation between warp triangle itself and the des crop triangle mask using CV2 bitwise and. Finally, the function returns the warp triangle, which represents the warped and masked triangle region. The warp triangle function takes a rectangle, rect, source points, point zone, destination points, point SWO, a source crop triangle image, SRC crop triangle, and a destination crop triangle mask, des crop triangle mask. It computes an affine transformation matrix, warps the source triangle image using the matrix, applies a mask, and returns the resulting warped and masked triangle image. This line defines the function add piece of new face that takes three parameters: new face, rect, and warp triangle. This line unpacks the values from the rect tuple into separate variables x, y, w, and h. These variables represent the top left corner coordinates, x and y, and the width and height, w and h, of the rectangle. This line extracts the region of interest, ROI, from the new face image using slicing, new face y, y plus h, x, x plus w. The ROI corresponds to the area specified by the bounding rectangle. This line converts the new face rect area to grayscale using CVT color function. It converts the image from the BGR color space to grayscale. This line applies a binary thresholding operation to new face rect area gray using CV2 threshold. It converts the grayscale image into a binary masked triangles designed, where values above the threshold, 1, are set to 255, white, and values below the threshold are set to 0, black. The CV2 thresh binary INV flag inverts the binary mask. This line applies a bitwise an operation between warp triangle itself and masked triangles designed using CV2 bitwise add. This line adds the warp triangle to the new face rect area using CV2 add. The addition is performed element-wise, which effectively blends the warp triangle with the corresponding region in the new face image. This line updates the corresponding region in the new face image with the modified new face rect area, effectively replacing the original pixels with the updated region. The add piece of new face function takes a new face image, new face, a rectangle, rect, specifying the position and size of the region of interest, and a warp triangle image, warp triangle. It extracts the corresponding region from the new face, converts it to grayscale, creates a binary mask based on the grayscale image, masks the warp triangle with the mask, adds the warp triangle to the region of interest, and updates the corresponding region in the new face image. This line defines the function swap new face that takes four parameters: dest image gray, dest convex hull, and new face. These lines create a binary mask, face mask, initialized with zeros, having the same size as dest image gray. The dest convex hull is used to fill the convex polygon, the face region, in the face mask using CV2 fill convex poly, resulting in the head mask. The CV2 bitwise not function is then used to invert the head mask to obtain the face mask, which represents the background region. These lines create an image, head without face, by masking out the face region in dest image using the face mask via CV2 bitwise add. This results in an image where the face region is black, masked out, and the rest of the image is preserved. Then, the new face is added to the head without face using CV2 add to blend the new face onto the destination image. These lines calculate the bounding rectangle, x, y, w, h, of the dest convex hull. The center of the face region is then determined by finding the coordinates at the center of the bounding rectangle. This line performs seamless cloning using CV2 seamless clone. It takes result as the source image, dest image as the destination image, head mask as the mask indicating the region of interest, center face as the location to place the cloned region, and CV2 mix clone as the cloning method. The function returns the final result of the face swap. The swap new face function takes a destination image, dest image, its grayscale version, dest image gray, the convex hull of the destination face, dest convex hull, and a new face image, new face. It creates masks to separate the face region and the background, blends the new face onto the destination image, calculates the center of the face region, and performs seamless cloning to produce the final face swap result. This function takes an image as input and sets it as the source image, SRC image. It then converts the source image to grayscale using CV2 CVT color, and stores it in SRC image gray. Additionally, it creates a mask, SRC mask, that has the same dimensions as the grayscale image and is initialized with zeros. The code calls the getLandmarkPoints function to obtain the landmark points of the source image face. These landmark points are stored in SRC landmark points. The landmark points are then converted into a NumPy array, SRC NP points, for further processing. The convex hull of the landmark points is calculated using CVT convex hull and stored in SRC convex hull. Finally, the convex hull region is filled with white, 255 pixels in the SRC mask using CV2 fill convex poly. The code calls the getTriangles function to obtain the indexes of triangles formed by the landmark points within the convex hull region. The convex hull, landmarks points, and NP points parameters are passed to the function to calculate the triangles. The resulting triangle indexes are stored in indexes triangles. The setSRC image function sets the source image and performs pre-processing steps such as converting it to grayscale, creating a mask based on the convex hull of the face landmarks, and calculating the triangle indexes within the convex hull region. These pre-processing steps prepare the source image for further operations, such as face swapping or image manipulation. Global SRC image, SRC image gray, SRC mask, SRC landmark points, SRC NP points, SRC convex hull, indexes triangles. This while loop runs indefinitely. The global keyword is used to indicate that the listed variables, SRC image gray, SRC mask, SRC landmark points, SRC NP points, SRC convex hull, indexes triangles, are global variables that can be accessed and modified within the loop. These lines read a frame from the video capture, cap, read, and assign the result to the variable dest image. The underscore is used as a placeholder for a variable that we don't need in this case, typically used for the return value of a function that we're not interested in. The CVT resize function is then used to resize the dest image to the desired width and height. These lines convert the dest image to grayscale using CVT color with the CVT color BGR2 gray conversion flag. The resulting grayscale image is stored in dest image gray. Additionally, a mask, dest mask, is created with the same dimensions as dest image gray and initialized with zeros. These lines obtain the landmark points of the face in the dest image using the getLandmarkPoints function. If the dest landmark points is none, indicating that no face was detected, the loop continues to the next iteration. Otherwise, the landmark points are converted to a NumPy array, dest NP points, and the convex hull of the points is calculated using CVT convex hull, storing the result in dest convex hull. These lines extract the height, width, and number of channels of dest image and store them in the variables height, width, and channels. Then, a new image, new face, is created as a black image with the same dimensions as dest image using NP zeros. The code sets up the main loop for processing frames from a video capture, resizes the captured frame, converts it to grayscale, creates masks, obtains landmark points, and initializes a new face image. The exact purpose and usage of the new face image and the global variables depend on the remaining code that is not provided. This code snippet is a loop that iterates over each triangle index in the indexes triangles list. This line calls the triangulation function with the triangle index, SRC landmark points, and SRC image as parameters. It returns points, triangle vertices, SRC crop triangle region from the source image, crop triangle mask, mask for the crop triangle region, and an underscore which indicates that the return value is not needed in this context. This line calls the triangulation function with the triangle index and dest landmark points as parameters. It returns pointsflow, triangle vertices, an underscore, not used, dest crop triangle mask for the crop triangle region, and rect, bounding rectangle of the triangle in the destination image. This line calls the warp triangle function with the rect, points 1, triangle vertices from the source image, points 2, triangle vertices from the destination image, src crop triangle region from the source image, and dest crop triangle mask for the crop triangle region in the destination image. It returns the warp triangle, which is the triangle region from the source image warped to fit the corresponding triangle in the destination image. This line calls the add piece of new face function with the new face, rect, and warp triangle as parameters. It adds the warp triangle to the corresponding region in the new face image. This loop performs a triangulation process for each triangle in the indexes triangles list. It obtains the triangle vertices and crop triangle regions from the source and destination images using the triangulation function. Then, it warps the source triangle to fit the corresponding destination triangle using the warp triangle function. Finally, it adds the warp triangle to the new face image using the add piece of new face function. This line applies a median blur filter with a kernel size of 3x3 to the result image. The median blur filter is commonly used to reduce noise in an image. These lines obtain the height, h, and width, w, of the src image and calculate the scaling factor rate by dividing the desired width by the actual width of the source image. This is done to resize the source image for display purposes. These lines display the source image and the new face image using OpenCV imshow function. The src image is resized using the calculated scaling factor rate before display. This line writes the result image to the result1 video writer, which was initialized earlier to save the output frames as a video. This line displays the result image, which is the final composite image with the swap face regions. These lines wait for a key press and check if the pressed key is ASCII code 113. If that key is pressed, the loop is exited, terminating the program. This line closes all open windows created by OpenCV, effectively ending the program and closing the display windows. Okay, now I will test the project. I will try to put Ronaldo and Messi in my face. Okay, deepfakes work successfully. Thank you for watching the video. Bye bye.